Now we are going to derive what is known as the Flexure formula. So previously, if you remember, we have derived the formula for the axial loading, the torsion formula. So now we are going to specifically look at the case of bending that is there. Now, if you remember, where we had left off was this beam which we were looking at under pure bending. So you have an M and an M over here, and some of the assumptions that the plane sections remain plane before and after bending and so on, and also the top part contracts and the bottom part expands. That is, the top part is in compression, the bottom part is in tension for the case where you have the sagging moment, and in between you have a line which does not undergo any tension or compression or change of length, and that is known as the neutral axis. So in this beam, maybe let us mark this particular line that you see, this dotted line. Let's say that is the neutral axis for our beam, and there are ways to find this neutral axis that we will take a look at later. So we have this neutral axis where there is no tension and no compression, the length remains the same. Now before this beam, before you have applied this moment M, this beam is straight, right? So whether you're looking at a length of dx at the neutral axis, or whether you're looking at top or at bottom, the length of each of these smaller chunks is equals to dx that we have over here, right? But the moment you are applying these bending moments that are there, after that the length of the line along the neutral axis stays as dx, because remember, neutral axis is that line which does not undergo any change of length, right? So that length of that line stays as dx. But if you take a line which is above the neutral axis, essentially in the region where you're having compression, that line contracts. That we had seen that the top part of the beam, the upper half of the neutral axis, undergoes compression, the bottom part, the bottom half, is undergoes tension, that is there, right? So now let's start to write some of the formulations that we may get that when we are looking at these kinds of beams which are undergoing this level of bending. So now, as we discussed, so if we mark some of these points which are there, this EF, I'm looking at this line segment EF over here. So the original length of EF that you see here is just dx, because it has not gone any deflection. So the original length of EF is dx that we have, and which is, again, if you have to write dx, which was originally, it was dx is the same as the length of this neutral axis, and the length of this line segment along the neutral axis has stayed as dx. But now in terms of this d theta and in terms of this radius of curvature, remember rho is the radius of curvature, I can write dx as nothing but equals to rho times d theta. Right. Now let's take a look at the same line EF again. Now this line EF, what is the deformed length of EF? Now this EF is at a distance y from the neutral axis. So this is at this distance y, and after it has bent, after this beam has bent, this EF has undergone a shortening. That's what we have seen, that above the neutral axis the lines undergo shortening. So, and what is going to be the length of this EF over here? That can also be easily calculated. That is going to be rho minus of y times d theta. So EF is going to be rho minus of y d theta. Now if we have to calculate the longitudinal strain for the line EF, how do we find that? What do we mean by strain? Strain is the change in length divided by the original length. So if we have to write that, that becomes equals to, so the change in length will be rho minus y d theta minus rho d theta. So it will be minus of y d theta, and the original length is your dx that we have over here. So it is going to be minus of y d theta divided by the original length dx, that is rho d theta, times rho d theta over here. So that becomes equals to minus y divided by rho, and we know that 1 divided by rho, or 1 divided by the radius of curvature, is simply the curvature kappa. So that is equals to minus of kappa times y. So my epsilon x becomes equals to minus of kappa times y. So this is an important formulation that is there. Sigma we know that my sigma is related to E times epsilon. So this is from Hooke's law, which we know already. right? So how does sigma x vary? So sigma x, now see, you see that how beautiful this concept is. We are looking at the bending, but we are looking at normal stresses and strains, right? So there our sigma x becomes equals to minus of E epsilon x, which is equals to minus of E kappa y. So what does that tell you? That tells you that from both, if you take a look at this expression or this expression over here, right, it is a linear function of y. So what does that mean? That means that as you are moving away from the neutral axis, your strains increases and correspondingly your stresses also increase in a linear manner, right? It's a function of the kappa y. Now remember, this is valid only within that limit of proportionality that you have. If you're going into the non-linear region of the stress strain curve, this does not hold true anymore. This is only valid within the proportionality limit of the Hooke's law. So let's maybe make a quick note of that one, that stresses and strains, so sigma and epsilon varies linearly with distance from the neutral axis. Neutral axis is NA. So here also, let's just mark it. This is my neutral axis, NA over here, and this is NA. Right? Now, the important thing to note over here, that when y equals to 0, that is y, remember, is the distance from the neutral axis. When y equals to 0, then your strain is 0, stress is 0. So at the neutral axis, no stress, no strain, and that is the reason why the neutral axis does not go any contraction or elongation. It just stays what it is. Above the neutral axis, you are having a compression. And also very important to note one thing is the reason why we are getting this negative sign. This reason why we are getting this negative sign is that we have considered a point which is on the above, which is undergoing compression. So that's why if you look at that original where we are getting this negative sign, it comes over here. So the change in length is actually a compressive change in length, and as per convention we mark compressions as negative. Now suppose if you were taking this line below, this would come out as positive. So don't be too bogged down by the signs, as the sign means that sigma x is compressive. Here negative means sigma x is compressive, and epsilon means that it is undergoing shortening in length. If it's a positive, that means that it is undergoing tension and the section is undergoing an elongation. So that's the only reasoning behind this particular sign, and no other reasons. If you understand the logic, you get a hang of it pretty soon, right? So now this is the general formulation so that we get. So if you have to just summarize quickly, what we got is that, and this is a great way to visually see. So you see this entire section, what was plane over here, this section was this rectangle. After bending, the plane section has remained plane and it has just bent, something like this over here. Now as a consequence of that, at the middle line you do not have any stress or strain, right? So about this neutral axis, so you have essentially this plane, this is the neutral axis which is undergoing. So you have a plane along the length of the beam which does not undergo any change of length. No compression, no tension, but as a consequence of this section moving like this, you can see that the top part it's very simple to visualize as well. So if you do something like this, you see the top part is undergoing a compression, bottom part is undergoing a tension. And how does it happen? Is that this is the general formula for that. This is you are having this compression over here, so you have this epsilon x, this change in length, and this is the part where you are having the tension. And another way to say, so you might be wondering in your mind that in the bottom part, will I get a positive or a negative? Of course you will get a positive, because you see, if this is your zero line over here, you're measuring from here, so your positive y you have measured vertically up. So if you are taking any point below that, you have substituted negative number over here, will be minus y, and you put that minus y over here, so minus of minus y becomes positive. So it is, so don't be bogged by the sign. So sign is just to indicate this is a compressive or a tensive. This is the general formula. If you're looking at places which are above the neutral axis, you have a negative stress indicating compression. Below the neutral axis, your y is negative, and if you put it back over here, you will get your sigma as positive. That is indicative of tension over here. Now, if you want to look in 2D, the same figure, for example, this one, if you are looking at from this particular angle in 2 dimensions, this is a good way to visualize this. And most of the textbooks now you're seeing, and later when you will study concrete design, you will see they represent it like this. So the top part, so this is again my neutral axis which I'm looking at. So let's just quickly mark that. So this is my neutral axis. Right. So above the neutral axis, you are having a compression, and below the neutral axis, you are having a tension that is there. So these are the two of the important relationships that we saw. Right. Now, next we are going to use these relationships again, especially the one for the stress, to derive what is known as the flexure formula. So let's go ahead and take a look at how to derive the flexure formula.